everybody. Today I'm going to talk to you guys about energy in sound waves. Now, energy has to have some place where it comes from. We have to be able to trace how it moves through a system, and then at the end we have to know where it ends up, where it goes to. And so as a result, we're going to kind of talk our way through that here real quick. It's helpful to remember the discussions we had when we were talking about pendulums. A pendulum, you did work to lift up the bob, and then that work was stored as potential energy, which then, when it was released, became kinetic energy as it fell down. And then because it had so much kinetic energy, when it got to its lowest position, it continued its path beyond and then became potential energy again. And in a simple harmonic motion situation, that would reoccur over many, many periods of time without any loss of mechanical energy. However, we know that in the real world, there is loss of mechanical energy to thermal energy. The friction in the system and the imperfections in the system cause some of the mechanical energy to become thermal. And as a result, over time, all of the energy is lost, all of the mechanical energy is lost to thermal. And so the system heats up, and it still has the same amount of energy it had at the beginning, but it's not something that can be used for the motion of the object. And so there's a reason why we did that first, because this is kind of a similar situation. And so I'm going to use the speaker idea here, because it's a little bit easier to visualize that a speaker, like the one you have here, creates sound waves in the air. So how does it do that? Well, I want to direct your attention all the way down here to the bottom here for a second. So I just drew the cone of the speaker as if it was a plate, just because I want to keep this as simple as possible. Now, all around the plate are air particles, naturally, because those air particles fill in all the empty spaces that they can get to, right? So the air kind of flows into it. That's why we call it a fluid. So it flows into this space that's right next to the speaker cone. Now, there is an electromagnet that's back here. You can't really see it in this diagram here, but there is an electromagnet, and that electromagnet has a set of wave or current pulses that go through it that cause electromagnetic fields to occur and then to change their shape, change their size, things like that. And as a result, this plate, or this cone, if you will, move back and forth due to that electromagnetic force. So what do? When the plate moves forward, is it has to move forward through all of these air particles, which I've drawn in blue here. To be able to move through those air particles, though, it has to apply a force to those air particles. And it applies that force over a certain displacement. And the cone, or in this case the plate, moves forward for a certain displacement and then moves backward. As it's moving forward, it applies a force over a certain displacement. And we know from our energy unit that a force applied over a certain displacement is the way that we define work. And that work then never goes away. It becomes some form of energy. And so in this case, you can see that we have applied work to all of these particles here. And so there must be some form of energy that occurs as a result of the work that we put in. And so I want you to think about it like this. So as you pushed those air particles, you gave them some potential energy. And as a result, they got all bunched up. Now you can see right here, this is what that would look like. So all of the air particles have been pushed together, squeezed together, if you will. So my question is this: do the air particles like to be squeezed together like that? It's like jamming 20 or 30 of freshmen into a closet. Not that I would do that. But if you would, what you would find very quickly is that they don't like that. And so as a result, they would want to get out. And they would want to separate themselves away from each other. And so the same thing with the air particles here. They don't like to be that close together. And so squeezing them together like that is only a temporary thing. And so as a result, they end up pushing each other apart. And so what you end up getting is the air particles that get pushed together end up pushing each other away. So I'm going to go ahead and draw this in here. So while they're temporarily squeezed together, they will feel very quickly a force that pushes them back into their original positions. So they want to get separated out there. And that force is like a restoring force, like the restoring forces that we had in spring pendula and in the regular simple pendula. And so as a result, they do separate out. But initially, they're all squeezed together, and so we have this potential energy. And then by separating out, they push each other away, which causes a force, which causes an increase in the speed of those particles, which gives them some kinetic energy. Now, they very quickly get bunched up with the particles that are over there, which give them another bit of potential energy. And this whole process repeats and goes back and forth, just like we had with a simple pendulum. If you'll remember, simple pendulum looks like this, like so. And up here we have a high potential energy, and up here we have a high potential energy because gravitation is pulling these down. And then down here we have high kinetic energy when it's at its lowest point. So this is a similar situation. It's a little bit more difficult to conceptualize, though, because it's lots and lots and lots of little air particles. So to create a sound, typically what happens is over time you get this plate moving forward and moving back and moving forward and moving back. And so it's creating this area of squeezed air particles or high pressure air particles that want to get away from each other. And so they get squeezed together and then they push each other apart, and squeeze together and push each other apart, and so on. And as a result, we end up with these kinds of waves that you see here, where they're squeezed together, we call that a compression. And where they are separated out, we call that a rarefaction. And then compression, there's a rarefaction here, and so on. You get the idea. Rarefaction just means a place where there's not a lot of air particles, where there's very few. And so you could say low pressure if you wanted to. So again, the energy in a sound wave comes from the fact that force is applied over a certain displacement. So, something to think about here. This space between here is a wavelength. And if you counted how many of these complete waves occurred every second, you could figure out the frequency. So, with that said, that works out. That's no problem. That works out pretty well. Then the question is, how does one actually perceive greater amounts of energy in sound waves? And that comes back to this. If I lift a pendulum bob up to a higher height, I have given it more amplitude. Amplitude is really the distance that the particle is away from its rest position. So right here, it's this distance between the rest position and the farthest point that it gets to. So if I did more work, in other words, I applied I applied the same amount of force over a greater amount of displacement, I would have done more work and therefore put in more energy. And so the energy is represented as the amplitude in the system. We hear that in the loudness of the sound wave. And so if you want to think about it this way, you can think about the fact that if the amplitude were greater, what you'd end up with is particles that were all very close together, like so. So they're in a very, very narrow band right there. And so as a result, you have much, much higher pressure. You guys have probably felt this if you've ever gone to a concert and stood in front of a speaker. You can feel the sound waves come off of a large speaker because they are basically wave pulses of really compressed air particles, which is pretty cool, I think. Anyway, so hopefully that helps. If you have any questions, please let me know. Thanks for watching.